Hello everyone, nice to have you here on this webinar about sorting black plastics with FX50. We are really delighted to be here with you, and this webinar is going to be in three parts. The first part is going to be an introduction, general presentation about Specim. Then there will be a live demo, and here you can actually see our demo system, and then the conclusion. About myself, I am Mathieu Marmion, working at Specim as a lead application specialist. And about Specim, Specim has been founded in 1995 and is a spin-off of VTT. All along those 30 years, we actually delivered more than 10,000 hyperspectral devices all around the world. About the world, we have global presences. We have some in the United States, here in Europe, in Oulu, Finland, where we have the headquarters, also in Germany and in Spain, and finally in China. We also have a network of distributors all around the world. Since 2020, we are part of Konica Minolta. Now about the live demo. Here we have the demo system, and I will show you how to use it, how to use the FX50 properly, so that you can use the camera as well in the lab, but also for industrial use in a conveyor belt, for example. So, let's first speak about what we see over here. It consists on the 100x50 scanner with the thermal illumination and also the camera. The name 100x50 is coming from the name actually of the sample tray and the size. It means that you can accept or you can put samples as large as 100x50 centimeters. And here we can see the samples we are going to measure. Here we have all the samples. We have three types of plastics. We have here sample made of PS, those made of ABS, those made of PE. And here some of them, they are like this, they are scuffed, they are really diffused. Some others, they are like this one, they are more specular, like shiny. And we have those for all actually our samples, and they are carbon blacks. Then about the white reference, this is the one we are using. This is sandblasted aluminum, and this is suitable for the spectral range between 2.7 and 5.3 micrometers. Here you can see that on our demo lab, now I'm using what we call specular geometry. What does that mean? If you have a sample which is shiny, basically if you have the incoming light which is here, it is reflected exactly in the same angle but in the opposite direction. So then it makes sense to have the camera which is actually in the same, looking in the same opposite angle. And this is what we are having here. We are having one single illumination which is illuminating at 45 degrees and then the camera looking at the opposite 45 degrees. That means that when you have specular samples, this is working really well. Then the other type of sample, it is when they are diffused. Again, we see like this the sample, the illumination coming at a certain angle, but because this time the surface is diffused, the reflected light is in every direction. So the camera could be at the top, or it could be also with the 45 degrees. So if you have a mixture of specular but also diffuse sample, you need to have a specular geometry so that you can accommodate actually both types of samples. Here, this is a Specim illumination that you can recognize. It is one heating element. And now we have a single one to have illumination at 45 degrees and the camera on the opposite side. We could have both two heating elements illuminated twice at 45 degrees and the camera looking in between. Those geometry could be used, but since now I have diffuse and specular sample, I'm using like this, the specular geometry. Another aspect is very important. It is a white reference. The white reference allows the user to measure what is the incoming light seen by the camera, meaning taking into account also the transmission of the optics and the sensitivity of the detector. This white reference this time is not made of Teflon, as it will be between 400 and 2500 nanometers, but it is a plate of sandblasted aluminum, like here. This is a white reference that we are using. This white reference, if you are in the lab, of course you can measure it every time you are measuring your samples, but I understand that if you are using the system in an industrial environment where you have a continuous running belt, you cannot stop the system to just measure the white reference when you want. So the white reference, as mentioned, measure what is the incoming light seen by the camera. So if you manage to have a stable environment, meaning that if you have the illumination which is robust and also the system which is robust to the ambient illumination or ambient, how can I say, environmental condition, then you don't need to measure it that often. Another part of the system which is really important, of course, it is the camera. The camera which is here. This camera, this is the FX50, and it measures the spectra between 2.7 and 5.3 micrometers. This is a push broom camera. Like all Specim camera, this is a push broom, and it means that it measures the spectra only over a line, and each pixel of the line having independent spectral informations. In order to measure an object, you need to have a movement, so that's why we use a scanner. So line by line, you can reconstruct the hyperspectral cube, or then you could have a conveyor belt. This camera is having 640 spatial pixels per line and could be used with the full spectral range at about 370 frames per second. If you are not willing to use the full spectral range, but if you want to reduce the spectral range to what you think where you have the spectral feature of interest, you can do that, and the camera can even go faster. This camera is over the spectral range. As I mentioned, it is between 2.7 and 5.3 micrometers. So in order to protect it and to keep his radiometric behavior as constant as possible, we recommend to put it in a temperature stabilized casing. This temperature stabilized casing would first protect the camera from the dust, because typically if you're in a recycling environment, you can have a lot of dust. So if you want to prevent from abrasion, or if you want to prevent just the dust to stuck on the front objective, we recommend to have those temperature stabilized casing, and we recommend to have it below 25 degrees. For example, around 20 degrees, it's a good level to keep the camera. Also, it needs to be rather stable. Why is that? Because since we're in the thermal world, even the front objective is emitting. In order to keep the emission of the front objective constant, you need to have it temperature stabilized. Of course, as you can see, all the optical parts of the camera are already inside the casing of the camera, and this is already temperature stabilized. But still, the front objective is still exposed, and in order to keep like this emission constant of the optic, please keep it in a stabilized temperature casing. So basically, 20 degrees is good, up to 25 is okay, but I would say 20 plus minus 1 degree, this is quite good. Also, as you can hear, in order to have the camera sensitive, the detector needs to be cooled down, and there is a steering pump. And like every time you have a steering pump, it means that you have a mechanical movement inside the camera. In order to keep it long-lasting and working for a long time, we recommend you to have also this part of your sorting machine which is isolated from vibration. If you would start to have vibration, even small ones, and too often, I would say like all the time, then it may damage the camera and it will prevent the camera to be used for a long time. I could speak one more aspect about the illumination. It is the level of the temperature, and one parameter which is important to keep in mind. When I discuss with people about the usability of our camera, this is a thermal camera for sorting black plastics, they ask me, do we need to heat up the samples? Actually, no, you don't want to heat up your samples, because if you heat up your samples, they will start to emit exactly at the same wavelengths where you actually absorb. So it means the spectral feature will vanish. So you don't want to heat up your samples, but you want to measure them, you want them to be under the illumination. And here we are using an illumination which is based on an alloy element, a heating element, alloy rod. And in our case, in this case, it heated up to 650 degrees Celsius. So this is the illumination we are using. Of course, you need to have the sample moving underneath, but you don't want to heat up the samples. You just need to have a movement. So that was the introduction about the setup by itself, the scanner, remember, the sample tray, the sample by themselves, the white reference, and the camera. Since I am in the lab, I don't have the temperature stabilized casing which is necessary, because in fact the temperatures, ambient temperature is quite constant. I have to say next to this illumination is quite warm. So to use this, I'm going to use our software, Lumo Scanner, which is here to control the acquisition parameter with the camera, so we can adjust binning, integration time, frame rate, and also to control the movement of the scanner. And here I have adjusted a workflow so that the dark reference will be taken, there is a shutter inside the camera, also the white reference will be taken, and finally the data will be acquired. And then there will be a normalization. After I have done this acquisition, we will look at the data together with our software inside. So first, about the data acquisition. So here we have the acquisition software, and I can move here the scanner as I wish. I can look at the white reference as well here. And then we can see we have an integration time which is 0.5 milliseconds only, and we managed to fulfill quite well the well capacity without saturation. And then we have the possibility to adjust the workflow, like here setting up the white reference, like measuring the white reference, also taking the dark reference by closing the shutter. Once we have adjusted all the parameters, where to start the scan, where to stop the scan, we can just give a name to the dataset, webinar, like this. And then we can just press record, and the data are saved. So remember, this is a line scan device. So here, line by line, the sample will start to appear here on the waterfall view of the acquisition software. So now we see the PE, and the data are now acquired. It is as fast as this. Now we're going to move to the insight with the data analysis. Now, let's have a look to the data we just acquired with the Specim processing software inside. I will make a model. Maybe first we can have a look to the data. So here I double click. It opens in the Explore view, like this. Then we can zoom in it and we can make some selections. So here we had a first type of plastics. This is a PS. This is a diffuse sample. And here we have a specular one. We can recognize actually the spectrum of the PS. Then if I go to the next one, we have here some ABS. And normally there should be some feature exactly here around 4,480 nanometers, something like this. And then finally here we have the PE, which is completely different. And again, here we can really see that there are some nice spectral differences which can be seen like this with the FX50, but those could not be seen with the NIR camera, which is up even to 2,500 nanometers. So for black plastic, it's really mandatory to go up to those spectral range to be able to see those and to separate them. So then, to make a model, let's load the data set into the training, like this. We can zoom and make some selection. So for instance, I will select some diffuse but also specular samples because spectra are slightly different, so it would be nice to take those slight difference into account. So here we had first the PS, then the ABS. Just loading the selections. And now we can do with the PE. And then here we're going to take part of the background, which is a wooden board here, which is very different from the materials themselves. So then we're going to have 7 classes. The last one being, in fact, for the background. Like this. And it's going to be in black. And then I will make a class for each of those plastics, but also one for the diffuse sample and one for the specular one. So first it was a PS, it's going to be specular. Then it's going to be the PS but diffuse, and I will sort it with the same color as actually the specular, because at the end of the day it's going to be both PS. Then here it's going to be ABS specular, and then here it's going to be ABS diffuse, again with the same color. We put it in blue, like this. And the last one, it was a PE specular, and then for the PE diffuse. And I'll put them more like in pink, like this, because then it's very different from the PS and the ABS. That way. Then for each of the selection, we need to tell what is what. So the first one, it was in fact the PS specular, then the PS diffuse, and it was the ABS specular, then the ABS diffuse. Same with the PE, like this, and then the last one about the background. Now we have allocated for each selection a class. Then since we are having already 7 classes, I would increase the amount of, maybe not 10, the amount of latent variable in the PLSD algorithm. And then we can make a test already right away from here, and we will see which kind of sorting we get. So at the first glance, we can see that the PE could be now sorted pretty well, but then between PS and ABS is not perfect. So remember, there was only a small differences between those two samples, so it's good to add a little bit of pre-processing. And typically for the black plastic, I like to have some Savitsky-Golay as well as SNV. So if we put like this already with the first order derivate, then we will see if we get something better. And already from here, at least the PS looks much better, ABS as well, and then as well the PE. Then there is another aspect for the FX camera which is important, is that it's possible to make some selections, so you don't need to base a model on the full spectral range. But if you see that the most important spectral features they are here in this case and also here, you can put those, you can highlight those to be part of the model, then to really focus on those, and also to make the spectral range of the camera more narrow so that the camera can be faster. And limiting the amount of band like this can also make the processing of the data faster. So we can try to have a model here, so I need to increase by 1 the size of a band selection. And here we can see actually the results, they are not bad. Still some sample could be a bit misclassified. So here, one way to advocate this could be maybe to make more training selections. So we have seen here the classification. So we had some issues with this sample. So here we could make a selection, and that was some ABS, and this one was specular, like this. And then we can also see that, for example, the background classification could be a bit improved. So we'll take that, specifying that this is the background. And here we can try. So here we have a model which is performing rather well. So really, like, it highlights the capability of the FX50 to use the spectra to sort like this the black plastics. And once you're happy with your model, it could be then loaded into a processing platform. So this is what you can get. Another thing you may consider is dual integration time, because the black plastics, they have a much lower reflection than actually the white reference. So we actually recommend to acquire the data with the black plastic with a longer integration time than with the white reference, and this needs to be taken into account when you are doing the normalization. This is supported by Specim Insight. So you have seen the live demo, and from the data processing with Insight, you have seen that it's possible to sort black plastic with the use of the FX50. If you want to use it in an industrial environment, you have actually two options. The first one is to use Specim One. Specim One, it is our complete platform where you can actually make your model. You remember, you have seen Insight. So once you are happy with your model, you can then convert it into an application that you can load into a processing platform based on a GPU. The camera could be attached to this processing platform, and the output of it, this is not spectra anymore for each pixel of the line, but this is classes. So this platform is called Specim One, and it has the processing GPU, also the processing software. If you are willing to use a camera only, there is this possibility. It is provided with a SDK, a software development kit. By the way, the SDK is the same for every camera. So if you have made your solution already based on another Specim camera, to move with the FX50 is straightforward. So this is with the SDK. And you have noticed it is a GigiVision camera. So if you want to use your own GigiVision SDK, you also have this possibility as well. So now you have seen the introduction. You have seen also the live demo. And now I'm back to the studio somehow. And if you have samples that you want to measure, or if you want to make a feasibility study, us to conduct a feasibility study, please do not hesitate to contact us at info@specim.com. I also encourage you to visit our website, specim.com, and then we will come back to you. And now we are basically ready to go for the Q&A. So if you have any question, please stay in. Thank you.
Okay, so here I can see that in the chat, we start to have some questions. That's great. Thanks for the presentation. Yeah, sorry, we did our best with the technical issue we have. Do you have to do anything special? It's moved. Anything special to install the FX50 in the Lumo software? Well, no, basically you just install the Lumo software and then you choose, like you can choose which camera you want to install, which parameters, then you tick it, and then you have the possibility to install it just on your, on Lumo. Be aware that with Lumo, this is actually a Gigi camera, so we prefer to use, the SDK from Pleora. So basically you have our Lumo based on the Lumo SDK, and the Lumo SDK here is based on the Pleora SDK. So that means that there might be a need for a license as well. What's the type of light source? So the type of light source, it is actually a thermal illumination. So it needs to be a thermal illumination between 2.7 and 5.3 micrometers. And here, basically, you cannot use halogen, but typically we are using like heater, which is like an electrical barbecue. I'm really used to compare with that because I think that's the closest to what people are used to see. And this is heating up to, let's say, 650 Celsius. So this is actually like what Harry is now showing. Notice that we have also some gold-coated mirror. So actually, you can actually focus the light. But this is the light source we are using. You cannot really use halogen because it doesn't, provide enough illumination for this spectral range. Could you please show the difference between different plastics in spectra and clear better a difference made by specular reflection? Okay. So the spectra, we had actually one of the slides, but I know like here it's a bit difficult, but on the video you will be able to see them. Typically, the spectra, they are very different between the different type of materials. So if you want to sort PET, PP, ABS, PS, and many others, basically with the FX50, the spectra will be really different. But this is true that when you have using a diffuse illumination with a diffuse sample, you will not have exactly the same spectra as specular sample with a specular illumination. The spectra, you may have some derivative of it sometimes. So for example, between the diffuse and the specular one, you will see, for example, with the ABS, the peak at 470 nanometers will be a little bit different in its shape. And also the general trend, of the spectrum might be a little bit different as well. If we have a very thin plastic sample, like the one of a plastic bag, how can I prevent it from molding during inspection? That's a good point. That's true that this plastic, you may have the problem that it's touching the illumination, so you may put a protective things in front of the illumination, could be a grid, a mesh, or whatever, so that first of all, it doesn't touch the heating element. Having said that, the grid will get hot, and then your plastic, your thin film may touch it and melt on it. So that you have to be careful with it. I have to say, like for like this type of sample which are flying, you have to be careful because you don't want them to melt or you don't want them to trigger any fire as well. So typically for like black plastic sorting, I have seen flakes to be sorted, but not actually like a thin film. What is the smallest size of the sample you can measure? Well, with the FX50, we have three types of lenses. We have 24 degree, 45 degree, and 60 degrees. So typically, if you actually use a 24 degree lens and you focus it at the minimum working distance, it's about 30 centimeters, then you will have a field of view which is about 13 centimeters. You have 640 spatial pixels, so it is like 13 divided by 640. I would just do it. Just a second, I open the calculator on my computer. So 130 divided by 640. So you could have a pixel size which is about 200 microns. So I would say, I'm used to say the sampling should be at least 3 times smaller than the samples you can actually measure. So I would say up to 0.6 millimeters you can measure. But it depends, of course, of the size of the belt and the field of view. So if you have a bigger field of view, you have bigger pixels. So then the minimum object, I'm used to say it's about 3 times the minimum pixels. Yep, so I see we had, yeah, here I have the next question. Hello. Whether FX50 can be used to detect fire flame. Yeah, if you have in mind, for example, if you have a forest which is burning and you have the smoke and you want to see behind, I will not use this camera. I would rather use like a camera which is between 1000 and 2500 nanometers because the severe spectral range is suitable to actually see through smoke. So for fire detection, I would rather use like this type of device, but not really the FX50. What is the material of the light source strip? Yes, that's a good point, actually. There are different types of manufacturer here, and you can find actually light source made of quartz, and I would not recommend that type because the emission of the quartz within this spectral range has a dent, which is at about 4480, 4470 nanometers, and it is exactly at the same place where actually ABS is having a peak also at 4470 nanometers. So it may trigger actually some false alarm for the detection of ABS when you want to sort it from PS. So I would rather recommend like a heating element made of alloy, made of metals. That's actually the best. What is the lifespan of a camera refrigerator? This is true that this camera actually needs to be cooled down at the cryogenic level. So that means that the detector is cooled down with a stirring pump. And the stirring pump is having a lifetime. So first of all, it depends how often you turn on and off the camera, how often you power cycle it. Then it also depends like on which ambient condition you use the camera. So if you use the camera in a warmer environment, then the stirring pump will have to work even more, so to cool down the system. So it means like it's going to be even more demanding. So actually, we always recommend to use the camera in a temperature stabilized casing between +5 and +20. I don't remember if it's 20 or 25 degrees, but anyway, around 20 degrees is a good one as an ambient temperature, and it will expand actually the life cycle of the cooler. So the one we are using typically mentioned like a lifetime about 10,000 hours. But it depends like this on the conditions that you are using it. Have there been any application of the FX50 to look at concentration of spatial distribution of additive in plastics. Yes, it has been used, for example, for flame retardant or like glass fibers or like a different type of material. But I have to say it doesn't work for every additive that you have been put inside the polymer. We have seen customers using it for that. For example, for some flame retardant, it works. For some others, it doesn't. So yes, you could try, but it cannot detect everything. It's the same, with all our hyperspectral cameras. So basically, if the additive doesn't have any spectral signature actually along the spectral range of interest, then you will not be able to detect it. Is there any reason for the tilting in the FX50 and not the lights tilting? What is the camera? Okay, what if the camera is tilting? I think you refer maybe to the picture when it was in specular geometry. So in that respect, the camera was tilted to be able to see, the specular signal of the illumination. Illumination was at 45 degrees, and then the camera had to see the signal a little bit like a mirror. So that was for the specular geometry. But when you are in diffuse geometry, you have the light source at 45 degrees, and then a bit like my head here, looking straight underneath. So I think this is what you were meaning. So if I have specular samples, they act as a mirror. So in order to be able to see the reflected signal, you need to put the camera so that it sees as a mirror. I think this is the point of the question. FX50 for fire flame, I already answered. Do you have any suggestions, for the protective panel material you mentioned? You mean it was for the illumination? So for the illumination, you could use a mesh, you could use a grid. I will not recommend actually to use like a windows, because you could use which is transmitted over the spectral range, for example, germanium. But that's going to be extremely expensive because you need to have a big protective windows that you put in front of actually the illumination. That's extremely expensive. So either you put the illumination a bit further away, or then you put like a mesh in front of it, for example. If you think about putting the camera within a temperature stabilized casing, it is a casing as well. And here I would say if you over pressurize it, you just need to make a small slit where the camera is seeing through. And then if it is over pressurized, no dust is supposed to go inside. So you don't need to put actually like a material in front of it. What are the power requirement and operating temperature? The power, well, I have to say, I don't remember the power by heart. So here I would say, please go to our website and download the data sheet. To the best of my memory, this camera can be powered with 24 volt DC, but I do not remember what is the power consumption. Here, I must say, I don't recall. So operating temperature is +5, +40 degrees. But then we recommend to use it between +5 and 25 degrees to enhance, to improve the lifetime actually of the cooler. What are the parameters of the imaging array and what is the specs? So the imaging array, the material, it is made of MCT. It is a cooled MCT detector. And here we actually use, it is a 640 spatial pixels, in the spatial direction. And then the light is dispersed over 308 pens. But we recommend to use a binning by 2 because only with optical resolution, it is 35 nanometers. And in order to match binning and sampling here and resolution, it's better to use a spectral binning ×2. So then you will have a sampling which is about 16 to 17 nanometers, which is actually matching with optical resolution. It is a 16 bits camera, so it means data are coded between 0 and 65,000 and a bit more. So this is what you get. Yes, this is what I can say about the specs of the array. Which plastic you are detecting? Can we differentiate different materials? Yes, typically our customers, they use it to sort like PE from PP. That's really easy to do. Also ABS from PS, possible to do, a little bit more challenging. We have seen people using it as well for PCABS, PA, PET, POM. This camera could also be used to sort like different type of rubbers. So yes, as long as it is, other device cannot do it because it's carbon black. Typically, this one can do it. And actually, we have an article on our website. So if you go to specim.com, there is a search menu. If you type plastics, then you will find an article and you will see actually like how the spectra look like for different wavelengths and different type of materials. Would it be possible to detect polyethylene or polyvinyl? Polyethylene is PE. Polyvinyl, I'm not sure which one is it. Is it PVC? PVC could also be sorted as well. Can FX50 has the ability to identify metal? Not really, because metal, typically they don't really have molecules. So if you have some oxide, then it could. But if you have the pure metal, not really. But the FX50 is really suitable to detect different type of contaminant on metals. It could be like glue. It could be glue or different type of adhesives. It could be also oil, different type of lubricant. So it could be used for that as well. Thanks for the presentation. So you're welcome. How can you ensure that after calibrating with the white reference, the spectrum you measure is actually the reflectance spectrum of the material? Do you do any validation measurement? Also, how long does the calibration usually last for? So, well, actually here you ask a question which could apply to everything about spectroscopy, like the hyperspectral camera measure what is the reflected light. So then you need to take a reference, and then you can make this ratio, what is reflected compared to what is incoming, and you assume that with the reference, this is actually what is incoming. So we use what we call a white reference. So with a spectral range between 400 and 2500 nanometers, we use Teflon, and we assume that the reflectance is 100% over the full spectral range. This is an assumption. This is not always the case. There are some wavelengths that there are some little bit of absorptions. But when we are talking about this camera, the FX50, we are using some blasted aluminum. I have to say the spectrum is rather flat, but it is true. It is not at 100%. It's more like a gray reference, which is more like at 80%. So in that respect, I can say that the spectral features are correct, but maybe their intensity compared to what it should be like theoretically is a little bit different. And how long does it last? Well, you need to consider what can affect basically the illumination, like the white reference measurement. So basically the illumination. So if your illumination is changing, that means that your white reference is not valid anymore. Also, what you need to take into account is like when you measure the white reference, it is seen by the camera. So if you change any acquisition parameter within the camera, then the white reference is not valid anymore. Meaning, like if you change the binning, if you change the integration time, if you change also the frame rate or even the reading mode, ITR versus IWR, all of those will have an impact on the white references. So if you change anything, then the white reference will not be valid anymore. So then if you are making a sorter, you need to take that into account so that it stays as constant over the time. Another thing, by the way, to take into account, and it was your question, how long does it take? You don't want to heat up your sample, neither to heat up your white reference. Because when you're in the thermal world, like you have a material, and then it has some wavelengths where it absorbs the light. And it is what you measure actually when you have the reflectance, and you see some absorption peaks. But if you consider the black body theory, a perfect absorber is also a perfect emitter. So that means that if you heat up your sample, it will start to emit at the same wavelengths where it actually absorbs. So that means that if you heat up your samples, the spectral signature, in fact, will vanish. So you don't want to heat up your sample, and you don't want to heat up neither your white reference because it will start to emit as well. So not only reflect. So that's something to take into account. So you should be quick in making your white reference measurement. Thanks also to the camera, which is really sensitive. Typically, the integration time per frame, it's about 0.6 and 1 millisecond. So if you want to acquire 50 to make, for example, an averaging, it goes really quickly. Okay, that was not a question. It was thanks, Mathieu. We still have time for some questions. So does anyone want to ask anything else? Yes, one more question. It's more, okay, it's a bit more blue sky. What is the current barrier for pushing pixels resolution smaller? Do you think we will see hyperspectral getting into a range where we use focal plane array, FPA, chemical imaging approaches? Well, you know, for this spectral range, when you build a hyperspectral camera, you have to look at detectors which are available. So we are using a detector already, which is having like 640 spatial pixels in the x-axis. In the y-axis, we disperse the light over 308 bands, so I mean pixels. So I don't remember the exact size of the matrix, but here the pixel pitch, it's about 15 micrometers. So this is what is available. So of course, it's possible to use smaller pixels, but if you use smaller pixels, it means that you need to have an optics which is more resolute. So that means more expensive. So that means, like, first of all, you need to find a detector for this spectral range with smaller pixel, meaning price will get high. You need to have a better resolution as well for the optics, meaning better optics for this spectral range, price getting also high. Well, I could imagine that in the future, there will be like detector which allow you to do these kind of things, but then the price will be maybe a bit prohibitive. So this is, I would say, the current barrier, what is available actually. Can you measure through glass? Well, if it is normal glass, no, because basically it's black for this spectral range. So, but if you use like a glass like germanium, for example, then you can see through. But there are some cool applications, by the way, with FX50 and the glass. So with FX50, you can separate, for example, like normal glass from thermoceramic. So here there are like possibility for that as well. Is there any equipment for demo in China? So here I would say, please contact us in our sales team, and then we will come back to you about how to deal with the demo in China. Yes, you can win the lottery, and then we can chat to have the best camera ever with as many pixels and pen as you wish. Okay, do we have any more questions? I will wait maybe 1 minute, and if not, then I will stop. So okay, so maybe I will stop here with the Q&A. First, I would like to thank everyone really like for being here to attend this webinar. Oh, I still have a last one. Okay, that will be the last one, and then I will conclude. To have a more versatile, adaptable setup in an industrial context where the input material is mixed and potentially uncontrollable, instead of tilting the chamber and the illumination at 45 degrees for sample with high reflection, or positioning both perpendicular to the sample to capture diffuse reflection depending on the situation, will it make sense to use only, the later configuration, and for example, sandblast the sample? Or in an industrial context, would it make sense to have two chambers in series, each with one of the two configurations? Well, I think the first approach, if you have, let's consider the things. If you have a specular geometry, it means that you will be able to measure actually diffuse but also specular samples. But that's true that with the specular geometry, you have to be careful about also the positioning of your flakes, because if you are using flat flakes only, that's easy. But as soon as your flake will be tilted, then the 45-degree specular illumination will not reflect exactly where you have the light. So you could consider actually to have, maybe two illumination at different angles, and then the camera at 45 degrees. So then you can take into account also if you have your flakes, which is not perfectly flat. But so as said, so if you have a specular geometry, you can measure diffuse, but also specular samples. When you suggested we could actually sandblast or scuff the sample before to be sorted, actually this is what I'm used to recommend, because then the diffuse signal is actually higher in terms of intensity. That means the SNR is also better. But that means that you need to have a treatment of your sample before. That means that you need to put another cost. But yes, typically it's better to have like diffuse samples or to treat them so that they are diffuse. Of course, you could have like two systems, one after the other, specular and also diffuse, but I would say it doesn't make sense. So I would say maybe only specular if you do not want to have the shredder or the scaffer before. Regarding the problem of sample heating, what is a significant temperature variation for evident change in the spectrum? I would say like for the white reference, 10 degrees, and you can start to see the difference. For the sample itself, well, since it is a line scan device, it just go underneath. Maybe like, yeah, it's difficult. I did not try to quantify it, but I would say already 10 degrees as well, you will see the difference in the emission. That is a good idea to stabilize the optics temperature. Well, by the way, we do it for the SVIR camera, we do it for the FX50, and we do it also for the FX120 for the same reason I was explaining. Then the parasitic radiation is constant over time, and it is folded into the radiometric calibration. Yes, because then you can keep really the radiometric behavior of the camera, which is the same all the time, so it doesn't have any effect anymore. In fact, it is essential to stabilize the temperature of all the optics, otherwise the background radiation will fluctuate. Exactly, well, that was not a question, but that's also discussion between the participants is perfect. What is the required temp control of the operating environment is required? That's a good question. But first of all, this camera can work between +5 and +40 degrees Celsius. This is how we specify. But because inside the camera there is a steering pump, we recommend to use it actually between +5 and 25 degrees, because if you go for a warmer temperature, it's actually more difficult for the steering pump to cool down the detector at the cryogenic level. So we really recommend to use a temperature stabilized casing, which is between +5 and 25 degrees. And if you manage to have it like, let's say 20 degrees ±1 degree, it's even better, because it helps the camera in the process of cooling down the detector, in stabilizing the optics, so it makes actually the camera much more stable. So this is what I would recommend. Can FX50 identify metal? As such, metals, they don't really have molecules. It's more like when you have oxides. So when you have oxides and you start to have a molecule, then you can start to have like some spectral bond. But the FX50 has been used in the metal industry actually quite a lot to detect different types of contaminants that you could have at the top of the metal plate. So it could be like polymer, it could be oil, it could be glue. So here it could be really good for that. But for the metal itself, I would say not really, but everything around the metals, yes, there are some application. Can it operate equally well in the winter versus the summer in an unheated warehouse? Well, it's what I was explaining. It's better to have it temperature stabilized. As long as it is between +5 and +40 degrees, the camera will work. This is not a problem. Then it's more like if you want to keep the lifetime of the camera longer, we recommend to have it stabilized below 25 degrees, because there is a steering pump, and the steering pump has a lifetime. So if you if you use the camera always at high temperature, close to 40 degrees, it's going to be much more demanding for the camera. So it means that you will reduce actually the lifetime of the cooler. Thank you for the presentation. Exactly. What is the typical lifetime of the camera in hours? Okay, so it depends on the temperature, the first thing. And the second thing that it depends is how many power cycles you are doing. Because every time you power your camera, it means that the detector was at ambient temperature, so you need to cool down. So every time you power, actually, it's more demanding for the cooler itself. So I'm used to say that if you use a camera and then you go for the lunch or something like this, and it will take less than 2 hours, just keep the camera on. That's fine, because if you take a break which is less than 2-3 hours, it doesn't make sense to repower cycle the camera. It's better to keep it on, so actually you can save the lifetime of the cooler. But then it's what I was saying. If you take that into account and you use it between +5 and about 20 degrees, the lifetime, the MTTF is about 10,000 hours. Can we use SVIR and FX50 in a row in order to extend our spectral range, or is it difficult to the different lighting condition? Okay, you kind of answer the question. You don't have the same illumination. So that means that if you want to use the SWIR camera and also the FX50, you can put them one after the other. I have seen that to some of our customers, but then you need to have one illumination unit for one and one illumination for the other one. For example, for geological application, we have the CISO rock, and for the CISO rock, you can put several cameras at the same time next to each other, so you can actually measure like core following each other. And yes, you can have the SWIR camera, and then you can have the FX50. But as you said it yourself, you need to have two illumination units which are completely different from each other. Does the software quantitate the polymers in the stream or simply identify the type of polymer present? Our software, the one we have, which is working with Specim 1, make a pixel identification. So it doesn't even make an object identification, but it makes a pixel identification. So the output of the cube, basically, it's still a line. And for each pixel of the line, then you have a color which corresponds to a class to a certain polymer. So then after that, you take the output of the cube as an input in another system, and then you can do whatever you want. So if you want to count how many pixels you have or such a thing, that's a possibility. Then if you use the camera offline, then you do your model with Insight. You can also get a confusion matrix. So you can make a model and it will identify each pixel, what they can be. And then with the confusion matrix, you can actually deduce how many pixels are sorted as PPE, ABS, or whatever. And there is also a counter without going with the confusion matrix. What is the wavelength range of CO2 you mentioned that should be excluded in the model building? Yeah, I don't have it just by heart like this. I think it's 4,250 nanometers and 4,300 something nanometers, but you cannot miss it. If you look at the white reference, you clearly see basically the spectrum is rising because of the sensitivity of the camera is getting better and also the illumination. And then you have a clear dip, and then again, you have the spectral curve. So you just remove that one, but really it needs to be taken into account. How much more efficient is the camera when separating PP and PE than when using the full optical range? Well, actually, that makes a big difference because PP and PE, they're actually pretty easy to sort from each other. The spectrum of PE is really sharp like this, whereas the one of PE looks more like stairs like that. And this happens, the magic happens more in the range between 3,200, 3,500, maybe 3,600 nanometers. So if you want to sort PP from PE, you can reduce your range between 3.2 and 3.6 micrometers, and the camera can be not at 400 frames per second. I don't have just like this the answer to you what is the frame rate, but I could imagine 1,000, 1,500 frames per second could be done. Can the camera be used in an environment where there is water or solvent vapor? Well, you know, it's like putting a filter. So when you have the camera which is seeing through the air, and you put some vapor, if you put, different type of gas, it's like having a filter. So water could be problematic, especially if you have a protecting glass and then you have condensing water. So then it will be a problem. You will not be able to see through. Different type of solvent vapor, right, depend on your solvent, but you have to be careful because it's like having a filter, and that will prevent you basically to identify your material. Sorry, I take a class. Okay. Please explain and demonstrate the calibration of the illumination so it can be divided out of the detected signal. Sorry, I need to read it again. Please explain and demonstrate the calibration of the illumination so it can be divided out, okay, of the reflected signal. Do you use a diffuse reflector like sanded gold? That reflector also needs to be calibrated. So basically, what you are asking is about the normalization, if I understand well the question. So basically what you do, you take the white reference, which is sandblasted aluminum, in that case, not gold, because, well, that would be better, but that's also a bit expensive and more difficult to maintain, especially in an industrial environment. So we use sandblasted aluminum, which is reflecting up to 80% about. So basically, you have the camera, you put the white reference underneath, and then you just acquire the white reference. White reference, it is then the incoming light seen by the camera. So it means like with a given integration time, frame rate, reading mode, temperature, things like this. Okay. When you acquire the white reference, you need to be quick, by the way. You don't want to heat up your white reference, because if you heat up your white reference, then it will start to emit. So that means that it will damage, your white reference things. So this is the way you do it. So you take the white. Then to acquire the dark reference, you just close the shutter, which is inside the camera. So then you measure basically the reading noise. And when you do the normalization, you take your data, you remove the dark, and you divide by the white, which you have removed the dark. This is a typical way to do it. You can make as well a dual integration time approach. So that means that here you could use a shorter integration time for the white and a longer integration time for the samples, and then you have to scale with the ratio of the short time divided by the long time. But that's a possibility to do that when you have samples which are much darker than, in fact, you will have the white reference. You can improve like this your signal to noise ratio. Will an exterior windy environment cause operating problem? Yes, for the temperature stability. So you need to have the camera in a temperature stabilized casing. If you manage to control that, if you manage to keep the illumination as well constant, that's fine. But typically it's more like indoor, like recycling center. Outdoor, I have used sometimes the camera on a rotary scanner to measure, something outside, to measure gases or things like this. But not for like long sorting. So it depends what you want to do. You can use it outside. There are conditions for that. You need to have a black body. But otherwise, if you want to make like a sorting line, it's better to have it indoor. Can you share the slides? So actually, yes, the presentation will be shared by Harry with the video which was supposed to be played, and then it will be shared with you. Does the camera work well identifying a blend of PP and P when the gray-green is scared? So here I have to say I do not understand the question, because a blend of PP and the P, I don't know what is the P only. Maybe it was PE or PC. I'm not sure. And when the rain green is scared. So I have to say I have to quit this question. There, it's written after. No, maybe. Does the camera work well if there is organic stain on the regrint? Well, you can detect actually the stain. So it depends again what you want to do. Do you want to sort the polymer? Do you want to detect the stain? The stain could be like alcohol, it could be an adhesive, it could be like a glue, it could be different type of things. So it depends what you want to do. Question from Richard. It was, I think, 4.2, 4.4. It was the spectral range of the CO2. What is the smallest object you can detect? That's a good question. I'm used to say that the smallest object you can detect, it's about 3 times the pixel size. Why is that? Because if it is less than that, 2 times will work, but I prefer to be on the same side with 3. But if it's less than that, you have an object. And remember, we're in the digital world, so we are having pixels next to each other. So if you have pixels which are less than half normally the size of your sample, you will not have any pixel which will be covering only the sample and not the sample plus the background. So I'm used to say that the smallest object you can really detect and identify, really like to really get the spectrum of it and only of the object, it's about 3 pixels. Then the question, what is the minimum size of a pixel? So here, basically, we have 3 optics available with the FX50. We have 24 degree, 45 degree, and 60 degrees. So since we are talking about smallest object, I would take the lens which is the most narrow, and it can work at a working distance of about 13 centimeters. And then the field of view, the size of the line seen by the camera, it's about 13 centimeters. You have 640 spatial pixels. So 13 centimeter divided by 640, I think it's about 0.2 millimeter. Let me check quickly with the calculator. I will just do it. here. So if I take 13 centimeter and I divide by 640, yeah, it's about that. It's about 0.2 millimeter as a pixel size. So 3 times that, I would say 0.6 millimeters. That's the smallest one. Yeah. Yes, that is a CO2 bond. I agree. Does the camera work well if the blend of material is 90-10 versus 50-50? It depends. It depends on the blending. So if you have like two materials which are quite similar to each other, spectrally speaking, you will have difficulty to separate them from each other. But if you have like two materials which are quite different from each other, then if you make a blend, it's going to be easier to separate them. And also it depends also how you build your model, how you build your regression. So if you give like samples that you know really accurately what is the level of the blend, then you can make a more accurate model. Also, if you are making a model which is, for example, with samples 50-50, 40-60, 30-70, you calibrate your model with that. And then you give a sample which is like 20-80, not knowing in the model what is this kind of combination, is going to be more tricky. But here, if I can compare, for example, with what we do in fabric sorting with cotton and polyester, yeah, there are possibilities like this to make some blend, to separate the blend, because cotton is very different from polyester. But here it depends basically on the material you're looking at as well. Is the lifetime of the unit related to the camera itself or the MCT cooler? The MCT cooler. This is actually what is defining the lifetime of the device, because, you know, like the optical part, it's optics. So there is nothing which is getting damaged over the time if you use it in a correct way. So this is most of the issue with this camera. When you start to have issues with the lifetime, it is due to the MCT cooler. Does FX50 use for mineral or characterization sorting in industry? And if yes, what FX50 have more than the previous models, such as FX10, FX17, etc.? We have seen it used, especially on our Sisu rock, to identify like polycarbonate, if I recall well. So here, for the carbonate, yes. So here it's actually pretty good for that, for the quartz as well. So compared to the FX10, FX17, you know, it is more responsive to some different type of bands. So yes, it brings an added value. Then if it has been used for geological application in real time, like mining industry, to the best of my knowledge, doesn't come to my mind. But again, I don't know everything what our customers are doing with our camera. It might be, but I don't know it for sure. But anyway, if you go to our website, there is actually, like in the publication or the application part, there is geology. And there you have a table actually where you can see which camera, which spectral range is suitable for different type of mineral. And there you can see that actually the FX50 is quite good for different type of minerals. Is the shutter actively temperature stabilized? The shutter itself, no, but it is part of the camera casing where inside everything is temperature stabilized. So ultimately, the shutter is at the same temperature as the optics which is around. So it is, I would say, it's stabilized, but not actively. There is nothing on the shutter itself to stabilize it. You mentioned using a plastic white reference when measuring the illumination for normalization. Does Specim provide this white reference and the black reference, since both of these references will have its own mid-wave spectral reflectivity, not exactly one for white or 0 for black? For the referencing, actually, with the thermal camera, you have different schools. You have what we call also the cold reference and the hot reference. The cold reference will be basically not to have a shutter, but just the camera looking at the hole, and that will be at the ambient temperature. So that will be the cold reference, what we could call as well the dark reference. Then the hot reference is like what you mentioned, like for the white referencing. In our case, it is when we have the sun-blasted aluminum. When it is a kind of plastics, it's more like for the spectral range between 400 and 2500 nanometers. It's not really a plastic, it's more like a Teflon. But anyway, for the FX50, it is actually sun-blasted aluminum. And yes, it's about 80% reflectivity level. For the black, It's not zero. It's not zero, as you say, because anyway, when you close the shutter, if you look at the cool hole, you have the emission of the optics and you have the reading noise of the camera. So it will never be zero. And by the way, with this camera, the longer the integration time, the longer, the more you will integrate the signal actually emitted, by the optics. So you do not want actually to have a too long integration time with this camera, because if you do that, the effective dynamic range, what you could use to actually measure your signal, there is not that much left. So the good thing is that this camera is really sensitive when you use it with a thermal illumination. So you can use an integration time of 0.6, 0.9 milliseconds. So it gives you still a lot of dynamic left so that you can effectively measure your samples. But yeah, this is the way it works. But we supply the white reference tile, yes. What is the efficiency separation improvement when running a 3/8 inches pieces versus a 1? Oh, well, okay. So here I'm not going to make the calculation. I would say, please send us an email. We will come back to you. Thanks a lot for the insight. Have you used the tool as a mean to identify black specks on transparent visible plastic pellet like PC or PMMA? That's interesting because something which is transparent to the eyes is not necessarily transparent, for the FX50. So yes, I have measured PC, I have measured PMMA, and the FX50 is actually really suitable to solve them. They are not transparent in the long wave, in the mid-wave infrared. What is the cost for a replacement cooler? You need to contact our sales team for that and our support team. Can the FX50 sort between PET plastic and polyester textile? I haven't tried those. I have measured PET. Yes, I have done that. And typically the spectral signature of PET is very something which is like, it's clear. I mean, you cannot mix it with anything else. Polyester textile, I guess it's really close chemically from the PET. So actually, if it is exactly the same molecule, the camera should not be able to differentiate because the camera is just looking at the molecule. So if it was used for clothes or if it was used for automotive industry, if it was used for whatever, it's the same molecule. So at the end of the day, the spectral signature will be the same one. So I think not. Are there any more questions? I can wait a bit. Yeah, I can come back a bit to the question, like what is the efficiency separation improvement when running the belt? I have to say 5 meters per second, it's already pretty wide. Then you have to consider as well what is the frame rate of the camera. So you have the belt which is moving. So depending on the frame rate, you will be able to identify your sample or not. So if, for example, here I've been missing like my watch, I will come back to this graph, so in 1 minute, but first I finish my answer. It depends on the material you want to sort. It depends on the spectral range of the camera, which is enough or not. It depends a lot of parameters actually. So it's not so easy to answer just like this. So yes, here you can see actually the spectra of the different type of plastics that we have measured with the FX50. By the way, the FX50 could be used to measure black plastic, but not only black plastics, also if they are like white or whatever, but including black ones. And you can see like quite a lot of things happens around 3,200, 3,300 nanometers. There are quite a lot of peaks there. So yes, so this is how it looks like basically. And this is available on our website. Are you sensitive to texture? In a way, yes, we are sensitive to the texture because when you have a sample which is more diffuse, it means that there will be more light reflected towards the camera. In contrast with a sample which is more specular, where it's more like, on the opposite angle. So if you are like with a specular geometry. So yes, the texture could have an impact, I would say, on the intensity, but not really on the spectral signature. Surface texture, yeah, but I got the point. Thank you. Does it easily differentiate between HIPS and ABS? So I would say HIPS and PS are the same. So like, because high intensity or not high intensity, that I could not manage, but PS only, yes. And ABS, yes, there is a peak, as you can see here on the graph that Harry is not showing. ABS has a really nice peaks at about 4,500 nanometers that PS doesn't have. But except of that, PS and ABS before, it looks exactly the same, but it's just this difference at 4,470 nanometers. So yes, it works. Can you please tell if it can be used for mineral sorting? Yes, here it can be used. Again, on our website, there is like a table which shows like for all our cameras, like VNIR, SWIR, FX50, and FX120, which mineral can be sorted. Actually, Harry, since you are sharing screen like this, and if you could find this table, that could be interesting because there were already the question before about the usability of this camera for the mineral sorting. So
yes, I'll try to find it for you.
Perfect. He's like Big Brother, coming from behind. So it's perfect. So waiting for the table, is there anyone else having a question? Are there applications of this camera to artwork analysis, digitalization? Actually, yes. It is not the main application, but I have measured some paintings, some different type, of pigment with the FX50. So actually that you can really differentiate this type of, you can differentiate different type of pigments. And yes, there are some application here for this type of application. But here, you need to be careful about the source of light. It is a thermal illumination, so you have to be careful not to heat up your sample. By the way, when you use halogen, you have to be careful the same way because halogen also can heat up your samples. But yes, there are possibilities. For example, we have measured like this, like painting with our 100 by 50 scanner. And when it's moving under the camera, under the illumination, we have noticed that the temperature of the sample increased only by about 4 to 10 degrees, but not more than that. And you don't want to heat up your sample because if you heat up your samples, it will start to emit on the same bands where it absorbs. So if you heat up your samples, basically your spectral signature will vanish. Yes, thank you, Harry. This is the table I was looking at, asking for. So you can see it is on our application tab. It is oil and mineral exploration. And here you can see different type of mineral groups, some examples, and which camera is relevant where. So the mid-wave infrared is actually pretty good here for the carbonate. So I remember pretty well, but then here you can really look yourself at this table as well. And you will have the possibility to choose what is the right camera depending on your application. Will you be at Photonics West next week? Myself, no. Unfortunately, I will not be there, but there will be some of my colleagues. So if you have any question, please do not hesitate to drop by our booth, and I'm sure my colleague will be really happy to answer you. Do the pigment spectral signature get hidden by the polymer paint vehicle? Oh, I need to read again. Do the pigment spectral signature get hidden by the polymer paint vehicle? That could have an impact. Of course, like when you have a polymer mixed with a pigment, when you measure the spectral signature, you will measure like a mixture of those. That's really a fact. But it depends. I have seen like a different type of study. Actually, this is not only for the FX50. This problem it is like for everything. So when you are mixing your pigment with anything else, you have to think if the anything else will have an impact on your measure. This is something you have to take into account. Is it possible to detect chemical contaminant on plastic or fabric or paper? Yes, glue, oil. Actually, we made some application note here that actually different type of contaminant could be detected. What temp range of the in-fed sample is possible to feed to the camera? If you want to measure, it depends what you want to measure emission. If you want to measure the emissions, that it needs to be pretty warm, like maybe 100 degrees. If you want to measure reflection, you don't want to have it warm. So it depends really on the application you have in mind. So yeah. I will stop by the booth in Photonics Race. Thank you very much. Okay, so it seems that I have been speaking quite a lot. Maybe more questions. I can take maybe one or two more. No, it's okay, that's fine. So it was a pleasure again for me to make this webinar with you and to have so many people attending and to have so many good questions like this. Again, we apologize because we were not able to show the video which was planned with a real demonstration, but anyway, Harry will send you the link with this video so you can see how we operate actually the camera, and then it will explain again how to use the system basically. If you have any question, do not hesitate to drop an email, info@spekim.com, or visit our website, spekim.com, and we'll be happy to come back to you. So I wish you to have a nice evening, a nice night, a nice day, wherever you are, and I hope to see you next time on another webinar. Thank you very much.